Hello everyone, welcome to our video series on the architecture of business applications. We want to cover various things we've learned over the last several years. I founded this company called Remigis Technologies more than 2 decades ago, and all this time we have been building challenging large business applications for enterprise customers in the banking, finance, capital market space, government clients, etc. We have learned a lot about software architecture and their peculiarities, challenges in this period. So I thought it will be great if we cover some of these in the video series that we want to create. So let's get started. So first, what this series will cover and won't cover. Okay, we will not be covering front-end software. We will not be talking about the architecture of mobile apps, for instance. We'll only be talking about server-side architecture, because that's where we find architecture to be interesting and challenging, and it has all sorts of trade-offs and shades of gray and so on. So we will only be talking about server-side code. We will not be talking about programming languages. We will not be talking about these components which are used in the architecture of a large business application. We will not be talking, for instance, about whether RabbitMQ is good or Kafka is bad, or is the Kong API gateway the best API gateway, and so on and so forth. We are not going to compare products. And we will not be talking about cool architectural features or services of these public clouds like AWS and Azure. Okay, so those things are not to be covered. The stuff that we will be covering server-side software architecture. We will be taking a look at these typical classical terms with which architecture is discussed. Things like service-oriented architecture and things like that. What do those things mean? And we will be taking a kind of a deep dive into you can say the practice of architecture. How do we go about, quote unquote, doing architecture? Building a software application, implementing functional features is one side, and the architecture is everything else. So how do we do architecture in a kind of logical and systematic way? So that would be the meat of what we will be covering. Okay, how architecture is seen conventionally. Okay, when we look at architecture, when people talk about architecture, they throw around certain terms, and these become very standard, and they have sort of gained wide acceptance without being very well defined. So let's look at these terms. The first architectural concept is a monolithic architecture, a single mass of software. Now we will see that there are shades in that, but monolithic is one common term. The other term is the next idea is these n-layered architectures, 3-layer architecture, 2-layer architecture, and so on. Front end, back end, 2 layers. Application server, transaction server, database server, 3 layers, etc., etc. So that is one common term. The third term that we hear often, which is quite orthogonal to all these layers, is the service-oriented architecture. So what's a service-oriented architecture? What is a service? Then we have event-driven architectures. An event-driven architecture is an architecture where events happen, like messages come in and triggers are fed into the system, and the system reacts to it. So what the hell is that? Then we have microservices architecture. So all of these are interesting terms. This is a very conventional way of looking at architecture. Now, when you talk to people, you usually find people using these terms with great confidence, but we don't get the feeling that this alone is good enough. A discussion on architecture has to be much more nuanced. So, in practice, serious work in the area of software architecture needs to be much more nuanced, needs to have a blend of many ideas, etc., etc. So, the entire idea of how we look at architecture needs to be re-looked at from the ground up. Okay, so that's going to be sort of one of the things which I'm looking forward to doing in this series. I have this tendency to get into fundamentals and make sure my thoughts are clear, at least clear enough for me. So, the next question that I want to look at is, why do we need architecture? Now, why is it that we want to talk about this subject of architecture at all? When it's almost as if, on the one hand, we have these very trendy buzzwords like service-oriented architecture, microservices architecture. On the other hand, if you ask a person what is the foundation on which you want to start building your architecture concepts or your architecture design, there is non-clarity. So, why do we need architecture at all? So, if we want to understand this, we need to look at what would be the architecture of your software if nobody deliberately did any architecture specification. What would it land up being? So, that would be what I call a college student architecture. If a college student has learned Java and has then learned a little bit of how to build web applications, he'll be writing applications in Java and he'll be creating a jar file, and then he will be deploying it on his laptop and testing it out, and that would be something, right? That would be a working application. Now, if we have to understand why we need to do architecture, we need to understand what he does and what more do we need to do. If we don't understand that, we don't have a takeoff point without that. So, let's look at what architecture emerges by default when this Mr. College student or Miss College student builds his Java application. So, he will have one server, which could be his laptop to begin with, one server with one disk, and on that server there will be one database. Everybody uses some database or the other for the conventional business applications. One database, one Tomcat. We are talking about Java, right? So, we will talk about Tomcat as a typical application engine. So, all the code will be in one jar file and he will plug it into his Tomcat and get things going. So, things will work on his laptop like that. And one IP address for the server. So, the server will have an IP address and there will be one internet link. As in, if he wants to make his application accessible from the outside, this laptop will have to have an internet connection. So, this is the stack. One computer, we call it a server, one computer with a hard disk, one database, one Tomcat, one bundle of Java code implementing his web service calls, and one IP address. The entire study of architecture starts from one question: why isn't this enough? Why isn't the college student's default software architecture enough? If it is enough, then we can close this entire story and get on with building applications. There is no need for designing the architecture of your application if the default architecture serves all purposes. Okay, so this is the core idea. The answer to this question, why isn't this enough? The answer to this question comes from NFR, non-functional requirements. Now, to be able to understand what this is, we need to understand functional features versus NFR. So, everything functional is functional and the rest is non-functional, and non-functional requirements are the seed from which all the architecture challenges come up. So, to be able to understand all this, we need to understand what is functional requirements. Look at any business application, look at any application. Let us say a simple application where you are using the application to maintain accounts for your business. So you have a screen to enter vouchers, you have another screen where you'll see all the vouchers entered by other people. You will have a screen where income and expense entries are offset against each other, and you'll get maybe something called a trial balance, etc. Now all of these things are things you need to do with the software. Functional things. So these are the functional requirements of any business application. If you have some other application which, let us say, controls machines in a factory, so those will be the functional requirements of that software. It will turn on a machine, it will monitor the speed of the machine, it will switch off machine number 1 when machine number 2 is ready. Those are the functional features of that software. So every software has functional features. But in order for the software to be useful in large and challenging real life scenarios, which means not the college student scenario, in a real life scenario where there are many demanding, many demanding demands on the software needs to fulfill non-functional requirements too. This is the critical differentiation. So we will look at non-functional requirements. For instance, one of the commonest non-functional requirements is the throughput. What is throughput? Throughput is a technical term which we are all familiar with in our industry. It talks about the rate at which transactions, let us say, hit the system. So if the software is being used to record transactions, purchase transactions, then what is the rate at which the software needs to operate? That is its throughput. So if I have a throughput requirement for my software, let us say I have a requirement of 3000 transactions per hour. That is one kind of requirement. 20,000 transactions per second, that's a very different number. 3000 per hour is less than 1 per second. 20,000 per second is a phenomenal figure. So this is a non-functional requirement. Transactions will be handled by the software, whether it is 1 per minute or 1 per hour or 1 per second or 20,000 per second. So the rate at which the software needs to handle transactions is a non-functional requirement. The fact that it needs to record transactions is a functional requirement. Do you see the difference? So non-functional requirements are of various kinds. Let's just go through some more of these. Okay, what are the other typical non-functional requirements? Because this is where architecture comes up. The practice of architecture is born out of an appreciation of non-functional requirements. If there were no, as I keep saying, if there were no difficult non-functional requirements, college student architecture would be adequate. One laptop would be enough. So let's look at what are the cool non-function requirements that large enterprises throw at us with respect to their business applications. The second non-functional requirement example, NFR example, is peakiness of the load. Peakiness is a word we use which means does the load figure peak, as in does it show a sharp rise during a short period of time? So the opposite of peakiness is flatness. So if the software which we are trying to build or trying to run will experience load which is uniform for like 12 hours a day or 24 hours a day, that is a very non-peaky load. But real life business applications often show terrible peakiness. For instance, a trading exchange may say that they are handling several 100 million trades per day, which is cool in itself, quite impressive. But the peakiness takes it into a completely different level of craziness. They may say that 50% of the day's transactions are handled in the first 15 minutes and the last 15 minutes of the trading day. That's peaky for you. That's crazy peaky. So you can have peakiness in a daily cycle, you can have peakiness in a monthly cycle, a yearly cycle. I'll give you some very popular examples of peakiness in load. We all know that the Indian government runs a portal where we can file income tax returns. But how many returns are filed, do you think, during a typical day? So for most part of the year, the figure is 0. Nobody is filing income tax returns every day. Income tax returns are filed at the end of the financial year. And there, I am told that once the financial year ends, in India it is 31st March, so the 1st April onwards, we are theoretically in a position to file our income tax returns. Nobody files income tax returns on the 1st of April. Nobody is filing anything at that time. They are filing returns only in the last 3 days before the deadline hits. And there may be very good reasons for this. We are not getting into that. But my point is, the entire country's annual income tax returns are filed in 3 days. That's peakiness for you. Another example which is very common in the retail commerce sector in India is the Diwali dhamaka. The Diwali freak out festive season probably accounts for, I don't know, 30% of the year's retail sales. I think in the US you have, what do they call it? Black Friday or some such thing before Christmas somewhere, or before Thanksgiving. There is some crazy period of absolutely berserk retail sales in a very short span of maybe a week or 5 days or something like that. So there are discounts from the suppliers, and there are huge expressions of demand from the market. So that's peaky load for you. Now all this stresses out your software system. The third thing that hits software systems, which are a common NFR in the systems we build, are latencies. Latency refers to the time delay from the start of an operation to the end. For instance, if I want to see what are the available railway tickets before I can book a ticket, I should be able to type in my query and hit enter and see the results in, let us say, 3 seconds. So that's a 3-second latency limit. The team which is building the software knows that the customer, which may be the railway booking department, will refuse to accept the software if the software takes, say, 10 seconds to show this list. So that's a latency requirement, which is an NFR. So if you understand this, the expectation that you will show the available seats in the train, that is a functional requirement. You will show the available berths. The expectation that you will show that data in 3 seconds is a non-functional requirement. That's not functional in the language of software. Then there are NFRs regarding speed of specific subcategories of calls. For instance, there could be there could be certain calls which are triggered extremely frequently. There could be certain operations which need to happen within a certain amount of time, or which need to show data which is very current. For instance, a very common example, again in the world of banking transactions and so on. A shopkeeper bills my credit card and he doesn't trust his systems. He wants to see the last 10 transactions which his bank is showing against the credit card which he has, against all the credit cards which he is billing. So if he bills my credit card, he wants to see that amount showing up in his last 10 transactions. So he'll bill my credit card, and within 5 seconds he will go to the next screen and he will check the last 10 transactions, which means that the software has to accept my credit card payment and insert it into the transaction statement screen in a matter of 3 seconds. So there is a speed expectation here which can be very demanding sometimes. The next NFR, very common, is the data size. Are you handling like 10 gigabytes of data or 10 terabytes or 100 terabytes? The entire architecture changes if the data volume goes up by, say, 100x. The next common NFR is to do with data flow. How fast does data need to flow? Common example. If I need to replicate data from one data center to another, and I can do it every 6 hours, and it takes 10 minutes to do the replication, then that's a very easy NFR. If I need to do this every night and the data is in terabytes and it takes 12 hours to replicate, then we have an NFR challenge. That NFR is very hard to meet. So the rate at which data needs to flow from one place to another can change things very sharply. It can change your architecture a lot. The next NFR is very common in the enterprise, financial sector, etc., etc. Uptime. How long can the system be down? Can the system be down 1% of the time? This means that the system can be down for 3.5 days every year. Can you imagine any banking system which will give you only, the rest of the year available on the system, and it will be shut down for 3 days in the year? No net banking system in the world will accept this as an acceptable level of performance. So there is an uptime expectation. That's an NFR. So 99% uptime is useless for net banking systems. They need to at least do 4 nines or 5 nines, which is 99.99% of the time. So uptime and availability expectations are a very common NFR. The next one is to do with access patterns. I need to be able to access this data, but only from here and not from there. For instance, I am a manager. I should be able to access very critical confidential reports on the system, but I should be able to access that report only from the desktops in the office. If I log into the system from outside the office, I should not be allowed to access that data. So these are access restrictions. The data is the same. The report will contain the same data, but it will be accessible to me under certain conditions, from certain places, maybe during certain times of the day, etc., etc. So, that's an NFR. Then you have compliance expectations. Many countries have begun to talk about data residency laws. You build a banking system, the data related to the transactions of the citizens of my country must reside on servers in my country alone. You want to operate in 10 countries, you better figure out how that country's transaction data sits physically in servers in that country. My country's transaction data sits physically in servers in my country. That's a very common legal and compliance expectation which is coming up in many parts of the world today. Now, the moment you have data residency restrictions, you have to comply with them, and if you have to comply with them, the architecture changes. So this is another NFR. There are many other compliance related NFRs which happen. We'll not get into too many lists, but this is a very good survey of the flavor of the NFRs which hit the design and the architecture of a business application. The architecture of a software service is best designed by starting with the NFRs. First, check whether the college student architecture will do the job or not. So how do we check this? Look at the NFRs and see what throughput you get on a single server. For instance, if the expectation is that we will need to handle only 1 million transactions a day, that's a very small number for modern computers. 1 million a second is huge, 1 million a day is quite small. So if we need to handle only 1 million transactions a day, and during peak loads there will be 2000 transactions per second, not more than that. Now, if that is the NFR given to you, then the architecture has to handle 2000 transactions per second. This can be handled by one server comfortably. Modern servers will often not, even break a sweat to handle a few thousand transactions per second. So your architecture is simple. If your throughput requirements are much higher, the architecture changes. Then look at the data volumes. Will you be expected to handle very large data volumes? If you do, then the architecture has to reflect that. What about rate of data flow? Does data need to flow from one machine to another very fast? Availability. Now, availability is, again, as I was saying, we're talking about downtime and uptime here. When we talk about availability, availability can be at various levels, okay? When we talk about a large software application, we need to look at how failures in the system will impact the availability of the software. So, you have to segment it separately into various angles and look at the availability from different angles. The first angle is, how will the software be available if one server fails? Typically, whenever there is a real life application, the availability requirements for that application will not allow you to use one server. Almost any application will have an availability expectation, which will say, oh, you can be down for not more than 15 minutes at a time, or 5 minutes at a time, or 30 seconds, or whatever. But even 15 minutes, even half an hour of downtime is impossible to handle with one server. Like, if I have one server and I don't have a second server, then I have to repair that server. So it can take me anywhere between a few hours to a few days, right? So that impacts architecture. The second issue will be availability in the case of failure of storage. What happens if a disk fails? Then the third challenge will be, what happens if the network goes down? My server is okay, my disks are fine, but I can't connect to the server, I can't connect to the software because networks are down. So what do I need to do in case I need to take care of one network link failure? Access patterns. Will I be able to handle all the access pattern expectations by just having everything running on one computer? Will I need to separate out different parts of the data, different parts of the services into different systems in order to meet the expectations about access patterns? So from all these explorations will emerge finally a picture which will give you a foundation to build the architecture of your business application. So business application architecture is built on a foundation of NFR. Some basic points about architecture. We have sort of surveyed things. Now I'm sort of putting some of these things together. First point, very obvious, architecture is a non-issue. The college student architecture will work if NFRs are simple and easy. If the NFRs cannot be met with the college student architecture, then you need to start looking at things piece by piece. The next point to understand is architecture is application specific. One application will require one architecture, another application may require a very different architecture. So there is often a tendency to generalize, a tendency to say, oh, we prefer architecture type X. That doesn't work. That simply means that you are insensitive to what the application requires. So architecture is application specific. Architecture is also hardware specific. You know, the kind of hardware you are going to run your system on will often strongly influence the architecture of the system. To give you an extreme example, which is not very common these days, if I know that I have to build my application to run on IBM Z series mainframes versus if I know that I have to build the application to run on, you know, x86 family of Intel or Intelish family, Intel compatible family of servers, the architecture will be very different. With Z series mainframes, I'll have 1 or 2 mainframes at the most handling the whole load. With Intel servers, I can go into clusters of servers. That's a completely different architecture. So architecture is very hardware specific. Architecture is also software stack specific, which means, am I, building the am I building like the application on a data store which is inherently distributed? Am I building the application in such a way that it will, all transactions will hit a single database running on a single system? So software stack also changes the architecture. The architecture which is natural when I am building using PHP may not be the best architecture when I'm developing my application in Java or in Go. So the architecture is software stack specific. Architecture also changes when boundaries have to be crossed. So what are the boundaries we are talking about? If my system, if my final application has to run in 2 data centers or 4 data centers, the architecture will change, because I have to then figure out where data will be kept in each data center, or will I centralize all data in one data center. So boundaries are of various types. One example is the boundaries between data centers. Then if my final application has to run on multiple systems within the same data center, the architecture will change. Are these systems similar or dissimilar? For instance, if I have my transaction data on a Postgres database running on Linux, and I have my customer database in a Microsoft SQL server running on a Windows server, they are 2 different, very dissimilar data stores. They don't connect naturally to each other. So if I have these constraints, wherever there are boundaries to be crossed, boundaries to be bridged, they will have an impact on the architecture. So these are some basic points on architecture. We've sort of taken a quick look at a quick survey of the things which impact architecture. We'll go into details later. There are many episodes left. So I now come to something even more basic. We did a basic question, why do we need to do architecture? Now I'm getting even deeper, absolutely at the ABC level. What is architecture? What is the architecture of a software application? I'm asking this question not because I love to play a textbook or I love to act like a boring professor in a college class. I'm asking this question because I see non-clarity all around me. People just blend and merge different concepts which are applicable at different levels of the stack, left, right and center. So I thought it would be a good exercise for me to try to get into the basics and look at what my answer is to this question. What is architecture? Now, when I look at architecture of a software application, I define it partly by what it is and partly by what it is not. So architecture is not the code of the application. No, the software code that you write is not architecture. Architecture can impact the way you write the code, but that's different. Architecture is not the code. It is not the design of your web service calls at an individual level. It is not the design of, whether your table will have 55 columns or 57 columns. Those decisions are not part of architecture. It is not the functional features. It is not, for instance, issues like whether I will have a voucher entry permitted to everybody, or whether I will have a voucher entry which will be done by an accounts clerk and then will have to be checked and approved by a manager. These are functional decisions. Do I have a requirement for an approval of a voucher entry? Is a functional decision. This is not an architecture decision. So what is architecture? It's basically 2 things. The components which make up the final running system and the data flow among them. The components and the data flow. I'll give you an example diagrammatically. Now this next slide. Okay, this is not architecture. Look at this slide. What this slide is depicting is one box, the first box on the left hand side is order entry. So after order entry, what happens? The order goes to a manager for approval and the manager approves. Assuming the manager is in a good mood and approves the order, then the approved order goes to the next 2 functional areas. One area is it goes to accounts. So the arrow going up towards the right, it goes to accounts, and the accounts department enters that order into an accounting system. The other direction in which the order flows is it goes to the vendor, because I'm placing an order on somebody, right? So that somebody is the vendor who will supply me the goods. So order entry followed by order approval, followed by going to accounts and going to the vendor. This is a picture which shows how a business operation is performed, how something is done from one step to the next. This is not architecture. This is a flow of tasks. It talks about business operations. This is what we call functional specifications. This is the functional flow. This is extremely critical. This is what software is made of, but this is not architecture. So what is architecture? Look at this diagram now. This diagram has an order processing server and a financial accounting server. So it depicts two servers, an FA is for financial accounts, FA server and an order processing server. The order processing server is where orders go in, and from that order processing server maybe some data will flow to the financial account server. So there is a data flow being described. Maybe, I'm just showing you a diagram. If I write text together to go with the diagram, I will probably describe the data flow. So there is an order processing server, order processing database, financial accounting server with its own database. So there are two separate databases here, which clearly indicates that the entire data of the system is not in one place, it's in two databases, at least two databases, and we have a message bus, an enterprise service bus, which connects these two components in the system and allows messages to flow from one to the other. So this is a diagram of components and data flow. This is architecture. So the previous slide is functional, this slide depicts architecture. Now what's very interesting is we were describing the same scenario but from two different points of view. So there is an architecture point of view. These things are mixed up so often. As I said, if I had $1 for every time these two things are confused, well, I'm not that rich. So I guess the people who are confused about these things don't talk to me much. Or maybe they don't give me the dollars. So there is an architecture perspective and a functional perspective to look at the same software application. So architecture deals with components and flow of data. It does not deal with the operations which the user will perform on the system. That is functional. It does not deal with the contents of messages, the database schema. It does not deal with users and user profile. It does not answer questions like, for instance, the manager will be approving the order and then the accounts clerk will be entering the order. That is functional. That's not architecture. So I will give you two sentences now to show you the two different perspectives. Look at this sentence. The MIS reports are being generated by BIRT. BIRT is a reporting engine. BIRT running on the reporting server and are sent to the query system over the enterprise service bus. So the sentence talks about certain types of reports being generated using a certain software component running on server X and being transferred from server X to server Y using a connectivity component, which is the ESB. Now, when you talk about these things in this way, this is architecture. Now let's look at the next two sentences. The next paragraph describes the same sort of thing happening but completely from the functional perspective. Now, what does it say? The MIS reports are generated from the sales data and are viewed by the regional managers once a week. They show sales grouped by region and by product category. This is functional. This is not architecture at all. This is what software developers do when they write code. They need to know what the MIS reports will contain, who will view the MIS reports, and will the data be grouped by product category or by price or by region or by location or whatever. That's the stuff of the functional features of the software. So if you can see the colors, the blue sentence is the architecture perspective and the red-brown sentence at the bottom is the functional perspective. So this is, I hope I have tried to explain, this is the architecture of a business application. What is architecture itself is an area of confusion. Architecture is the other side of a business application other than functional. So what are we doing in this episode? In this episode, we are going to look at the typical architecture related tools that we as architects use to try to achieve certain results. Okay, what are the tools at our disposal? What are the things that we can do to that college student stack in order to deliver on all sorts of challenging NFRs? Okay, so the first thing that I'd like to do is look at a relatively larger applications stack, as in what are the pieces that are in place. Some of them are hardware, some of them are software, which comprise like a non-trivial running application. Okay, so let's look at the layers. So we're going to look at the layers from the outside in, as in the outermost is of course the internet, from where the front end programs, mobile apps, etc. hit the stack. So the internet. From the internet, the first thing that you hit in a relatively larger, I'm talking about, large enterprise applications today. So the first thing that you will hit will be load balancers, because you will want to make sure that your load is distributed across multiple machines, etc., etc. And if one goes down, things will fail over to the other, etc. So the first pair of boxes are the load balancers. These arrows indicate accesses coming from the internet. Now extending it a little further, each load balancer will hit API gateways. Okay, so we are only showing one of the load balancers here, drilling down further. The other load balancer will do the same, but now each API gateway will then hit application servers. Modern non-monolithic applications need API gateways. It's a little difficult to set things up without API gateways. So load balancer, API gateway, application servers. Now each of these green, blue colored boxes that you see is supposed to represent a physical bare metal server or a virtual machine or a container. We are not getting into that sort of specification, but these are application servers. They are communicating, these application servers, the code in the application servers is communicating east to west in a parallel, in a horizontal line, using an enterprise services bus or a message bus. Then finally comes the databases, the data store. Now if you look at what we are trying to show in the diagram, we have tried to picture a slightly non-trivial large application. So we are depicting here a situation where we have split the data into two parts, the data which is fast changing and the data which is not changing much. Typically master tables don't change fast. Various report and MIS data or summary data don't change much, but transaction data changes very fast. So we are talking about two databases so that we can optimize them for two different types of response and performance and so on. So we are saying that we have two databases, one for slow changing data, and one for fast changing data, transaction data. Okay. And then again, this is a typical scenario in the real world where we have large enterprise applications. We can have multiple mirrors of that data. So each database is actually not a single database, as in not a single instance of the database server. There are, say, 5 databases running on with 5 different copies of the database server, and the data is being mirrored across them. This mirroring can be done through master-slave replication, which is quite commonly available in most databases, or other means. Okay, so we have all these moving parts which together make up the architecture of we have not even gotten into the software related components of the architecture yet, but at a box level these are the components of the architecture which make up a large enterprise application today. This was just an intro, sort of to give you a flavor of the pieces we have to play with. Now let's look at the tools and patterns. What do we do? What are the tools we play with, and what are the typical patterns of responses that an architect uses to address the NFR constraints. So if you require huge throughput, the architect's first solution is to get multiple boxes parallel to each other, horizontal scalability, scale out as it is called, by adding more instances of the same processing units. Okay, there are limitations, there are issues there which we'll talk about later, but this is the first reaction. The second tool that you play with is use RAM instead of a relational database. Keep data in RAM if possible. So when you have huge throughput constraints, don't directly write each and everything that you need to directly into a relational database. The third kind of scenario is where you have latency expectations, where you need to respond very, very fast, or you need to complete each operation in a very small number of milliseconds. What do you do there? Okay. The first tool at your disposal is once again RAM. For read queries, keep the data in RAM, use the RAM as a cache. For database writes, there is a very powerful weapon which needs to be used carefully if you're doing it at application level, or can require a completely separate class of databases if you're doing it at the database level. And that's sharding the data. Sharding means splitting the data set into disjoint subsets. So if I have 1 million records, I may shard them into two shards, where one shard only has 500,000 and the other shard has the other 500,000. So in effect, there will be no data store there will be no database which will have the entire 1 million records in one place. So that is sharding. For peakiness of load, when loads are very peaky, which means you have low load most of the time, but extremely high load for short bursts, what do you do at that time? On the cloud, use auto scaling. One of the earliest appeals of these public clouds was that they gave you auto scaling facilities. You could spin up and spin down instances on demand. One step further, which actually makes auto scaling automatic, where you don't have to do any scaling, is you use serverless blocks. Serverless blocks could be of various kinds, but go serverless. In hard data centers, what I mean by hard data centers is a data center which you physically own and administer, where you have bare metal hardware to manage. In such hard data centers, you can think about warm standby machines which are running but are not actually executing your load. Maybe they are powered down or semi-powered down or working in low power mode, which you can spin up if there is very heavy load. Or you could have a pool of general resources from which you can automatically apportion some resources to handle the peak. I'm not getting into details here. This is a fairly high level overview of the things that one can do. There is one kind of peakiness where you might have different types of services or subsystems which don't all peak at the same time. So maybe, during annual closing of your books of accounts, your financial accounting system exhibits peak load. During maybe retail sales time, your Diwali dhamaka or your Black Friday, your retail sales system exhibits peak load, etc., etc. So if the peakiness is segmented, it is not all across the entire application, then you might be able to have a pool of containers which can then be spun up or spun down based on automatic orchestration. So containers are very useful in that kind of a situation. You spin up only a minimum number, keep them working, ticking away happily. When it's required, more instances of the containers can be spun up. What does an architect do when he has to handle very large data sizes? One of the things we find which is often not done is archiving of old data. I am looking at this e-commerce site run by one of these organizations, and they're using Magento, and they have 5 years worth of orders in the order table. Why do they need 5 years of orders? Every line item of every order for the last 5 years are sitting in that order table. So queries will become slow, data set size increases, etc., etc. Archive old data to hierarchical storage, and of course the cloud gives an absolutely awesome, unprecedented level of options for archival of data if you need to do long-term archival. The second option is take a different approach, do data lakes. Don't get into relational databases, keep raw data, use tools like Athena or other tools which will be able to deliver queries on the raw data formats themselves. Next come situations where you need to do very fast searches through a large database. This is another situation where we find it's good to step out of the classic mindset of the relational database with its ACID properties and SQL statements. You can choose to move data or replicate data into a non-SQL database. Elasticsearch is very powerful, very suitable for very interesting queries, sometimes more interesting than what you can do on relational databases, and they are faster. Elasticsearch is lighter. So move your fast searches away from your main database and often to a non-SQL database to get the benefits of speed and also reducing the load on your transaction databases. So these are some of the patterns you can play with. Other patterns, when you have requirement for high availability, the first reaction and the good reaction is to have redundant clusters of everything. So your application servers are replicated, your data is replicated, data stores are replicating, you have primary, backup, etc., etc. All of that this is the classic solution. We will get into the details of replication and redundancy sometime down the road in some of the other episodes. What about access patterns, where you need to enforce certain access patterns and you need to be very careful about disclosure of confidential data, etc., etc. There, the classic solution is to define circles, like layers of an onion. So the most confidential data is in the innermost circle. The circle just outside that will have a little less confidential data, and so on and so forth. So data itself is not stored all in the same place. Keep data in different circles depending upon security and confidentiality constraints. So there are various security professionals will tell you about defense in depth and how you can apply that, especially when you have layers and layers of access or controls between the outermost layer and your innermost data. One of the things we find very useful from the security point of view is to not keep all your data in one big relational database. If you do keep all your data there, then any intruder who somehow gets SQL level access to that database is able to pull out all the data that he wants, even the data that he doesn't want. He can do like select star on all sorts of tables and pull out data. He may just do a query to find out what tables exist and pull out data from those tables and so on. So it's a little difficult to implement defense in depth if all your data is in one big, handy, very powerful, very flexible relational database. So split the data into different layers, move them to different data stores. Then the issue of compliance. Where you have data residency laws, you have no option but to break up the data into multiple data stores. So one data store in each country. Of course, these public cloud fellows make it super easy because they give you multiple availability zones for their services in multiple countries. So you just click from a menu and your data goes somewhere else. So you can do all that, but of course, very often application code also needs to change, particularly when you're doing queries on the aggregates. The second constraint is forget me laws about data privacy, PDPR. So if a customer has the right to demand that you have to forget the customer in your records, then you should index your data appropriately by customer ID so that you can trawl through all your data stores of all kinds of data based on just the customer ID and then remove the data records which are pertinent to that customer. And you look at more sophisticated logging for compliance, because whenever there is compliance, it's a gray area how much you have to do to demonstrate that you are complying. It's easy to say, I have a compliance requirement. It's a little more difficult when the regulatory authority says, demonstrate to us that you indeed are complying. How do you prove it? So additional levels of logging for traceability are very useful here. So these can impact architecture, because sometimes you may need to have separate data stores, separate log repositories just to deliver on this compliance. Now we'll look at a common problem, which is one of the, I think, most popular challenges that architects face, which is horizontal scalability. How do you scale? Everybody wants to scale, everybody wants to talk about how they can scale and how they can handle huge volumes and so on. So what are the challenges here? One of the most basic steps is to separate code from data so that code can be replicated. See, the horizontal scalability involves replication. You replicate various units, whether it's data units or processing units. If you wish to replicate, if you wish to do this spreading horizontally bit, then your data cannot be with the code. Otherwise, your code will replicate and the data will also replicate, and where you needed one copy of the data, you will now have 5 redundant copies and there will be no data consistency. So you need to separate code from the data. This is not as obvious as it sounds, because everybody today will separate out the relational database data from their code. But there are all sorts of other data units which are not relational database data, which are often left behind or are strewn around in a mess. For instance, configuration information. We usually find that architects address scalability challenges by scaling up the application servers. Low-hanging fruit. I understand it's easy to do. It requires less thinking. So go ahead and do it. The problem is that it doesn't solve the performance bottleneck. Very often the transaction database is the bottleneck. Now in that case, you need to do a reality check. Okay, we did one trivial benchmark. One slightly high-end desktop with an i7 CPU, 26 cores, 32 gig of RAM, which is not a huge amount of RAM. We were able to push in 40,000 insert transactions per second into Postgres. 40,000 per second exceeds a lot of the transaction requirements of a lot of large applications which we've developed. So it's a very large number. So the first thing to do is the transaction database a bottleneck? Is what you need to check. It often is a bottleneck, and it is not necessarily because hardware is slow. If you throw hardware at the problem, it may not speed up, because look at the incredible performance fairly ordinary hardware is giving for transactions. So why are they slow? They are slow often because the transaction database is not just handling transactions, it's also handling queries, it's also handling all sorts of report generation, and there may be various other reasons for it. There could be hotspots. I'll give you an example of a hotspot. It's so customary for these business application developers to create a table where they'll have an auto incremented ID. The ID column will be an auto incrementing integer. What this means is, I will insert a record, the database will increment the ID somewhere. It keeps an ID variable somewhere, which it calls a sequence. It increments the sequence and it assigns the new value of that ID to the new record. I insert a second record, another value is automatically created and assigned. Now, whenever there are 20 different or 50 different streams of transactions hitting the database, everybody wants the next sequence, and that sequence becomes a bottleneck. So for higher throughput, you need to shard your data. If one database is not enough, and it is a transaction database, not a reporting or a query database, then you need to shard the database. But first, you need to benchmark your hardware. You need to actually see what is the raw performance you get from the hardware that you have and the database which you have. And sharding is not easy. It requires application code change unless you use database software which does the sharding internally inside the database itself. The next and much easier solution to transaction database bottleneck is to do read-only replicas of your database. Most databases allow read-only replicas. So single master, multiple replicas are supported. So all your updates, inserts, updates, deletes will hit the read-write master copy, and the queries will hit the read-only replicas. So when queries move away from the transaction database, the database has more power left to handle the transactions. So this is a very big help in situations where you are hitting database limits. The next thing you can try is caching. Caching immediately increase your scalability. You have to use caching a little carefully. It's not something that you can use blindly, because blind caching generates problems which we are not even getting into. Okay, so you can use caching intelligently. Use asynchronous databases. This is not used enough. This is a category of solution which is not used enough. Document databases, distributed databases often support asynchronous updates and asynchronous replication. What this means is that you can have a multi-master cluster of databases. So the data is actually spread across multiple servers, and you can update the database by connecting to any of the servers. And when you update a record, that record gets replicated across all the nodes asynchronously, not then and there, maybe after a few milliseconds or even a few seconds. So asynchronous databases which synchronize, which sort of replicate and synchronize asynchronously, they will give you a very high degree of scale up very often. They are not used enough, as I was saying. The other thing that you can do is separate out different types of loads, so that the bottleneck is then isolated into one type of load, and then you can throw all your resources at that problem and try to make sure that you have adequate throughput there. For instance, MIS reports and transactions. If you generate MIS reports from the same database as your transactions, then that's a case where one thing is probably loading the other and preventing the other from moving fast. So separate them out. Now we'll look at the horizontal scalability of a database, again at a high level, conceptual level, but to understand a little more graphically how things work. Okay, so we're going to look at the simplest to the relatively more complex data organization or data store organization and architecture. The simplest architecture is that college student architecture, which is one application server and one database, as the diagram shows. One box on top, one database below. The next level is your read-only replicas. So you have one database which is read-write, and you have multiple replicas of that which are read-only, so they can handle all your queries. So you immediately start splitting queries to the replicas and doing the updates on the master. And the third one is you split the data, shard it. So the diagram that is being shown here uses 4 databases. Your data set is being split 3 ways. So there are 3 shards. So those are the pink colored databases being shown. The application server is here shown as only one. It could be 1 or 10, but the point is one application server is connecting to all 3 databases for updates, and the data set is split across these 3. Now if you see these curved arrows going from below, all of them are pumping their updates to a 4th database, which is a read-only replica. So that read-only replica is an aggregate of these 3 shards. What this means is that for updates, you connect to one of the shards and push out your update. For queries, you don't have to hit 3 databases to do the queries and then aggregate the data yourself. There is already a 4th database which is holding the aggregate of all the data sets. So you can throw all your queries at that one and get your easy, the software development for developing such queries becomes simple. So this is what I am referring to here as level 2, sharded read-write data. So these are different levels at which you can get horizontal scalability if your database performance is the bottleneck. So that sort of covers, a quick overview of the tools available for us to play with architecture to address challenging NFRs. This episode is the first episode where I am getting into this zone of these conventional terms: service oriented architecture, this oriented, that oriented, etc. So here, as usual, I am guessing you are seeing a trend in my style. I try to get a little bit of conceptual clarity for myself into some of these terms so that I can proceed safely. So we all know the full form, service oriented architecture. What is a service oriented architecture? Oh, the system is broken up into multiple services. Very good, very good. What is a service? Oh, service is a part of the system. And that's where you begin to understand that people who talk confidently about service oriented architectures don't have much clarity about what this thing called service is. So let's try to drill down a little. When I started drilling down, I encountered a bigger problem. Forget service oriented architecture, what is the service itself? And then the reason why this word became complicated is because I saw that the word is being used in so many different contexts by my own colleagues without being conscious of the fact that the word is the same but the context keeps changing. So let's try to just look at the different contexts, okay? See, there is one big thing which is an application. I just use the term software application for it. So that's the overall big animal. The application can be broken up into services. I'm going to call it an application service. So from an application come a few application services. Then there is another term which again uses that magic word service. A web service is one endpoint or one function which is being called using a REST API. So a web service performs one small well-defined operation. Okay, so that's a web service. Sometimes people use the term AJAX call to refer to a web service, but never mind that. Web service. The third place where you see service is microservice. What is a microservice? So if these are not micro, then does it mean that the microservice is smaller than a web service? So all sorts of confusion immediately, raise their heads and we are in trouble. So we will get into this in a little more, in a little more systematic way now. So let's look at it diagrammatically. The application is one big thing. If I build a monolithic application, it will be one big box like this, okay? And a monolithic modern application will have hundreds of web services. But if I go into SOA, service oriented architecture, then that big monolithic application is broken up into, in this case, 4 different boxes, each is a service. We will still have to address that other question, what is a service? But we at least know one thing, we know where the concept of service fits into the larger scheme. An application is broken up into services, and now if we remove all the services and look at only one service in detail, inside the service or the service comprises a large number of web services. So an application service is made up of a large number of web services. Okay, so far so good. So what is a service? Definitions in the classic textbook sense don't exist, but I have a definition. I have a conceptual idea which helps me a lot. I think of a service as the software and the data store which implements one object class. If you know object-oriented programming, or if you at least have some idea of object-oriented concepts, you understand that there are object classes and object instances. So one service implements one class of objects in my view and other closely related classes of objects. I'll give you one example. If I have a banking system, then bank accounts are a class of objects. One instance of that class is one bank account. Now, when I record the details of the bank account, I may be keeping all sorts of information about that bank account in that record. That is one instance of the class called bank account. So there could be a service which implements the data store and the code to manage just a class of objects called bank accounts. We'll come to these examples more as we go along. In a banking system, bank accounts is one class. Okay, so it could be one service. Account holders or customers could be another class. So all the information about the customers will be in the customer service. I'm not talking about customer servicing. I'm talking about the software service which implements the data and code for managing customers. So what are the things that you can do there? You can add a new customer, you can delete an old customer, you can update the customer's email address and phone number, update his Aadhaar record, and so on and so forth. And there could be other associated subclasses which are attached to or closely bound to the class called account holder or class called customer. For instance, you could have a subclass called, not a subclass in the usual sense, an accessory class called address. Okay, so account holders, bank account holders are human beings who have addresses. So addresses will also be an accessory class attached to the main class, which is account holders. So this way you can have this idea of a service which is handling only bank account holders or customers. Counterparty banks could be another another class, another service. So everything to do with counterparty banks will be in that third service, and loans could be a fourth service. So you create a loan, so the bank gives a loan to you, a loan record gets added into the loan service. So all the loans are kept in one service called the loan service perhaps. So you can break up a banking system, which is a big monolithic or a big black mass of functionality, into sub-functions this way, conceptually based on classes of objects. Another example, e-commerce system. The items being sold in an e-commerce system could be one class, customers of the e-commerce system could be a second class, orders, actual orders, which have all these line items and a total and a date and all that, could be a third service, and customer support tickets, when customers complain to the company, those tickets could be a fourth service. So you can think about the e-commerce system as being, as having four or more services. So this is a service-oriented architecture. Okay. So let's look at it diagrammatically to get a clearer picture. In this diagram, we are showing the classic college student architecture, monolithic. Access comes from the internet, it hits the application code. The application code has a large number of web services. See, this is not service-oriented architecture. This is monolithic architecture. One mass of web services is a monolithic application system. It has one database. So the entire set of web services are reading and writing data from one web service, one database. Now this is not service-oriented architecture. This is just a scale-up. What have I done? I have kept the database common, but I have replicated the application code across 4 servers. Now all the application code is running on all of the 4 servers. So this is just replication. So I have not split the functionality. I have kept the entire functionality. It is still monolithic. It is just copied monolithic, replicated monolithic. This allows me to use 4 servers for application code, where previously I was getting only 1. So this is just a technique to increase throughput, reduce latency. It is not a change in the architecture from monolithic to service-oriented. Please understand this very carefully. If you don't get this, you will be in deep confusion. Okay. How do we know that this is monolithic? This is service-oriented architecture. The key difference is that a service is a service if it has its own database. So if you say that you are splitting a monolithic system into a service-oriented architecture with 4 services, it means you have to have 4 completely separate databases. So this is the crux, this is the key. Okay? Now, when you have 4 separate databases, it means that the data, the primary copy or the master copy of any data is only in one of the 4. The others can get copies, replicas, but if you want to update something, if you want to go to the authoritative source of, let us say, the bank account data, then you'll have to go to the bank account service. It will have all the bank accounts in its database, but other services may also have copies of the bank account data. So service-oriented architecture almost always, I cannot imagine it otherwise, almost always requires some amount of data replication from one database to other databases, one service to other services. So all data is primarily in one database or the other. Any data, any class of objects will primarily be in only one of the databases, but they may be replicated elsewhere. So the key difference between just a scale up and an actual SOA is that every service has its own private database. Each service gets its own server, it gets its own database, its own application servers. So the application code is executing in containers or servers which are dedicated for that service. Okay? East to west traffic is done using a service bus. So either a message bus or an ESB. ESB is a very common term. It's basically a software layer which communicates, which carries messages from one server to another. So service to service communication, including data replication, is done using ESB. And because your main application is now split into multiple servers, multiple services, you cannot expect the front end, the client code, the mobile apps and the browser front ends to now know, oh, I am querying the bank account service, so I will have to connect to the bank account server. Oh, I am querying the loan service to get loan data, so now I have to connect to the loan server. That would be a royal mess. So you cannot have the front end code being forced to know what your service oriented architecture actually is. Therefore, you have to hide this information, so you need API gateways. So I do not see how you can have a service oriented architecture without API gateways. Infrastructure layers are shared. What this means is, things like login, logout, authentication, authorization, creating a user account. Now, when you create a user account, you are creating it for the application, not for a service. You don't say, I'm creating your login account to log into only the bank account server, but you cannot log into the loan server. That seems a very peculiar way of running the application. So user data, the table of users, the authentication and authorization services are common. They are shared across all services. Logging, where you put your logs, the logging infrastructure should be common. Business rules, if you have a business rules engine, it will typically be shared. Other components also will be shared. And one of the common things we find is that master tables are used by everybody. The master table of PIN codes and the master table of countries, the master table of account types and the master table of depositories and bank branches and IFSC codes and ISIN, for share trading you have this thing called ISIN, master table of ISINs. All of those are master tables. They are maintained by one service and are replicated across all services, so that all the services can get access to the master data without doing inter-service calls. So this is how a service-oriented architecture is structured. So that was a quick overview of service-oriented architecture. What is a microservice? So we have talked about service-oriented architecture, and now we need to go into microservices, because If I don't cover microservices, my credibility is mud. Okay. So what is a microservice? Extreme answer to extreme scalability needs. When you want the highest possible throughput, you use microservices. So what is a microservice? You start with an SOA, service-oriented architecture. If you remember, with service-oriented architectures, we talked about how each service is made up of a whole bunch of web services, and that bunch of web services shares one database. So service number 1 may have 75 web services all hitting one database. Service number 2 may have another 55 web services hitting a second database, and so on, right? So you start with that in your mind, break up each web service call into a separate server, make it a separate service. Each web service call. Replicate the server if required, if you have requirements for a lot of throughput. So you can actually build a cluster of half a dozen servers for one web service call, okay? And each microservice has its own database. So what you're doing is you are dedicating one server or one or more servers, one physical server or one container with its own CPU resources, its own RAM, its own database for exactly one web service call. That's a microservice. And when you have microservices, see, a microservice is doing next to nothing. It can only respond to one web service, right? So it only knows how to do one thing, which means there are no brother and sister services which update any database of its own or provide a full suite of services, which means 99% of the action is happening outside the microservice. This microservice is doing exactly one thing. So where do you get the view of the other 99%? The answer is very simple. Data from other services needs to be replicated into the database of this microservice. So east-west replication, east-west communication using an ESB is mandatory if you want to do microservices. And when you have replication, there will be a slight latency, which means that I do a transaction, the transaction hits the transaction database in real time. Otherwise, the transaction commit doesn't even happen, right? And then suppose I have a reporting server, which is a microservice. So the latest transactions are going to get replicated to the reporting microservice, and then they will show up in the account statement. But there will be a latency of maybe a few milliseconds or a few seconds. So this replication, which is required for running a microservice stack, will introduce a slight latency. It is definitely going to be non-zero. So one of the common examples is show account statement. When I want to look at an account statement, suppose there are typical times of the month where all the savings bank account holders of a big bank want to see their account statement. Maybe it's the beginning of the month and they all want to see whether salary has been credited or not. So maybe for the first 5 days of every month, there is an enormous load on just account statement viewing operation. So one way of handling it is to carve it out into a microservice, because it's just one operation, right? You are not really doing a service. It's not all the operations related to a bank account. It is just view bank account statement, one operation. So carve it out into a microservice, give it its own database, and let it run. So conceptually it is part of the accounts service, but it is implemented as a separate microservice. So it is not part of the service stack. It is a separate microservice stack. So it can handle a very high frequency of read-only hits. And if you want even more throughput, you create replicas of the database and you have a whole cluster of servers. Now, I compare a microservice with a very high-end sports car. So you have to understand that a sports car is awesome in performance, but it comes with its costs and its complexities. All the parts are expensive. It's a royal pain maintaining a sports car, not a Toyota or a Honda or a Ford or one of those cars which are sold in hundreds of thousands. So this you'll probably have only 5 of these sports cars in your city, and there'll be only 1 or 2, if you're lucky, service centers who can maintain your sports car, and the parts will be unique. They will have unique shapes and unique constructions, and therefore you'll have to procure them at high cost. And all the things that you do for other cars will probably not be applicable to this sports car. So it will be a big separate headache to maintain a separate extremely high performance stack. So if you need that performance, there is no answer. But when you go in for it, make sure that you understand there is a cost associated with it. So this is a diagrammatic representation of the idea of a microservice. What we have tried to show in this diagram, what I've tried to show here, is 4 separate microservices, not one microservice. Each has one application server where the application code is executing and one database of its own. So this is a picture, this is just a simple conceptual picture to show 4 microservices, one web service in each. Now this is an interesting take on that. The first microservice has been scaled up a little. Database is still 1, but application servers are 3. So what I'm doing now is throwing more compute power at that microservice, because I can see that maybe the code that is executing in that microservice is too compute heavy. So a little more CPU power is required, but one database is good enough. So I'm sharing one database and I'm throwing 3 servers at the microservice. Okay, so this is the microservice picture. Why do you need a microservice and why you should not use a microservice? First, why do you need a microservice? The obvious reason is extreme scalability. There are other reasons. The glamour comes from scalability, but there are other important reasons why a microservice may be attractive in some situations. One of the reasons is partial service availability. If you have your application running on one server, the server goes down, the second server has to kick in and the entire application has to be restored. If you have your application running on a cluster of 15 servers, including 5 microservices, then each microservice can go down and the rest of the application can continue to work. 15 after all, right? 1 out of 15 down is still 14 up. So breaking up your application into multiple servers gives you high partial service availability. The third benefit of microservices is high granularity, fine granularity. So you can bring down one, do some maintenance, bring it up again without the rest of the services being affected. That one microservice will go down, I accept, but the rest of the application won't go down. So maintenance can be done in small pieces, Another reason for microservices is non-technical. If I have 10 microservices, if I have one big server with the entire application in one piece, then one software development team has to manage that entire application, which means the entire team has to coordinate and release patches, bug fixes, extensions at one shot in one release cycle. If I have 10 microservices, then I can actually employ 10 teams and each team can manage its microservice. So I get more scalability of the teams and more flexibility of managing separate release cycles. So this is basically the classic model of the object-oriented software architecture. So that's for the pluses. These are the reasons why a microservice is attractive. What are the minuses? My favorite minus is that I don't like too many moving parts. From a service-oriented architecture to a microservice architecture, I'm just adding more moving parts. So an entire service with 100 web service calls, an entire application service with 100 web service calls may run on one server. If I carve out 2 microservices from there, those 2 will run on 2 additional servers. So I now have my moving parts going from 1 to 3. for a small amount of extra separation. So this degree of separation is something I would rather avoid, if possible. The second problem is the problem which always happens when I have a highly distributed application. The more highly distributed it is, the more of a pain this angle is. Observability and traceability are a royal pain. When I have 100 microservices running on 100 different containers, trying to understand what went wrong where might involve tracing through 15 of these microservices ka separate logs. So observability is a problem. You don't know what's going wrong where because there are more moving pieces to track. Then the third problem is timing and latency challenges in a highly distributed system are very difficult to reproduce. So suppose you start getting complaints that sometimes this particular call is taking 30 seconds. Sometimes. How do you reproduce it? If it's taking 30 seconds every time, you can go and check and there it is. It will be in front of you. Either it is true or it is false, but there are no gray areas. But if in a microservices architecture, there are latency challenges which happen sometimes, it is because there are certain back-to-back moving parts which are either responding slowly or are choking somewhere or are getting into some temporary short-term locks, or there are some resource contentions which cannot be reproduced under testing. So timing and latency challenges are not reproducible. It's not a matter that we have timing and latency challenges. No, you can have latency challenges in a monolithic architecture also, but here they are not reproducible. Fourth point is that it increases latency. This may not be a concern. If you're using a microservice, it means you have factored in the fact that there will be a slight increase in latency and you're okay with that. But just for the record, I wanted to sort of put it in the list. And microservices means cross communication, the east-west communication as we call it, shoots up. Because you're from one service, from one container or one server running one service, you might be going to 20 or 30 services, whatever. So the communication to synchronize all of them goes up 20 times. That traffic shoots up. So your data center backbone had better be fast enough to handle that cross communication. So these are the reasons why you want to be very careful before you get into microservices. But unfortunately, as I said, when the solution to the problem is a sports car, then no Honda or Toyota will do a good job. So when it is genuinely needed, it is needed. We don't know what else you can do. Now we come to this term which I have heard being thrown around several times. Oh, we are building a microservices architecture for our so-and-so application. And I have often wondered what exactly this means. So I have to tell you the story. Okay. No, I think I'll tell you the story at the end of this. Yeah. Let me first explain to you what a microservices architecture is supposed to mean. Okay. So a microservices based architecture means that there are no services where one service has 100 web service calls. A microservices based architecture means that every web service call has its own container running its own processing and with its own private database. So you might have 500 microservices. That's the only way in which the term microservices based architecture makes any sense, because otherwise you may have a service oriented architecture or a monolithic architecture with 5 microservices in addition. So when you don't want to use the term in addition, then you mean that the entire architecture is microservices. So this is a really extreme situation. I cannot honestly imagine where this is needed. Having done very large enterprise applications for very large enterprises with very large throughput. One of our old clients is one of the busiest stock exchanges in the world. We know what high volumes, high throughput is. Not just from this client, but from many other clients. I cannot imagine where you will require the entire architecture to be microservices based. So I'm okay with microservices to be added to an existing service-oriented architecture. You have a service-oriented architecture with 5 services, and you throw in 4 microservices in addition to handle 4 extremely tight latency, extremely high throughput operations. That's perfectly sensible. But an entire architecture, microservices? So, where does this usually come from? These are the 3 things I have seen. One is, it's a pet project by an architect or a CTO who just loves the idea of having a microservices based architecture. Or it is a startup which wants to use all the buzzwords, data lake, AI, ML, microservices, name it, you have it. And they basically want to make their solution a buzzword rich architecture to attract trendy VC funds. And the third case is a really extreme application which I have never seen in large enterprise applications of various flavors which I have worked with. So let me give you this story that I was telling you about. So we were approached by this company which wanted to ask us to bid for a software project. So we inquired about their background and what they do and so on. It turns out that they were a startup somewhere, I will not tell you which region of the world. They were a startup and they were well on their way to commissioning the software development for their business. Broadly, they were in the fintech space and they would be doing some transaction processing. And their core team had 3 people, 2 of whom were business people, and the third one was their CTO, who had spent some 15-20 years in one of the very large global technology companies. So he was here as the technology member of the startup's core team. And when discussing their software requirements with us, they said that they would like a microservice-based architecture. We said, okay, great. So we were very impressed because if you're asking for a microservice architecture, it means you have the extreme high end of requirement for throughput and extremely low latency. So we were very thrilled that we were getting an opportunity to work on such high performance applications. So we asked them, what kind of transaction throughput or transaction frequency do you expect? So they said over 25,000. So when you've just heard them say that they want microservices and you hear the word the figure 25,000 transactions, you think at the very least 25,000 transactions a minute, if not 25,000 a second. So we said, wow, okay, 25,000 in, we just wanted to clear, 25,000 a month. And you can imagine our silence. 25,000 transactions a month. Okay, that's like 1,000 transactions a day, and they want microservices. So we have this problem. We try to be honest when we make a proposal. So we gave them a proposal and we said, we are suggesting that microservices will be overkill and a service-oriented architecture might be good. We personally thought monolithic would be fine. Their uptimes requirements, availability requirements were nothing to write home about, and they could be met with a monolithic architecture. But we said service-oriented, and if necessary, later on microservices could be introduced at a future date if they saw the kind of demands that cannot be met with an SOA. So they didn't give us the order, and we got the feeling that one of the primary reasons was that their CTO did not want to be told that microservices appeared to be inappropriate. So we don't know what to make of such people. So for such situations, I have used these words. An entire architecture using just microservices may be a pet project of a hobbyist architect or a hobbyist CTO, which means this is a hobby project for him. And there is nothing wrong with having hobbies, but logically, as a practitioner of architecture, it doesn't seem to fit. One of the common problems when using microservices is cross-service calls, synchronous cross-service calls. This is a big mistake. Synchronizing or collaborating across microservices should not be done by synchronous calls from the front end. They should be done at the rear by using the enterprise service bus, using asynchronous messaging, not synchronous calls, because the entire throughput advantage of high performance microservices is 80% lost when you start chaining microservices one after the other in a synchronous chain. So we have also seen those mistakes done, not in architectures we have personally worked on, but which we have read about. So the only situation where I can imagine you might land up with an architecture which you can then claim is completely microservices based end to end is a serverless architecture where you are using serverless computing like AWS Lambda. In that situation, where even there, if you are not using separate databases for each microservices, it is not a microservice architecture. If you have 100 AWS Lambda components, but they are all hitting a shared database, then it's not microservices. But that is the kind of benefit of doubt I can give you, that in some situations maybe you have pushed partly towards a full microservices architecture. Otherwise, the term microservices architecture simply doesn't make sense. So this is one of the popular buzzwords which I am sorry I had to pour some cold water over. This one is going to try to put together a lot of things which we have covered in the earlier episodes to try to address realistic looking case studies of constraints put on us, on our development and on our design teams by our clients. All of this is hypothetical. None of these actually refer to a specific real project, but we've seen enough projects by now to know what they look like, to know what kind of constraints hit real systems. So, the first one, the last 10 transactions challenge. Now, what is this last 10 transactions? I think I had mentioned it in an earlier episode, but this one will be a bit of a deep dive into it. Payment systems, payment processing systems collect payments from merchants. And a merchant will be talking to a customer, selling him some item, taking the credit card or UPI payment from the customer and pushing it into his system. So he might use a physical card reading machine, or he might present a QR code to the customer for a UPI payment, whatever it is. Now these electronic payments need to be cleared and need to hit the merchant's bank account, right? So even if the money doesn't get deposited in the merchant's bank account till tomorrow morning, the merchant needs to know that the card that he has charged a few seconds ago has hit the payment processor. So the payment processor is a third-party service provider, very often a separate company, sometimes a bank itself, which is processing all the charges from a particular set of cards for a particular merchant. So when the merchant swipes the card, the device talks to the payment processor server. The card swipe device talks to the payment processor server and registers the transaction there. Now what does the untrusting, skeptical, unsure Indian merchant do? Within 5 seconds, he goes to the other screen of the charge processing device, the credit card device or his payment terminal, and checks to see the last 10 transactions within 5 seconds. And he wants to see that last transaction show up when he checks the last 10 transactions. So every time he charges a card, he is looking into the last 10 transactions to see whether the charge he has just done is showing up or not. If the charge is not showing up, it means one of two things. the card is faulty even though the device said the charge had been approved, or the payment processor is running flawed systems. His systems are not, not giving the right results. In both of these cases, the merchant will become distressed. So this is a very real business requirement. What does a payment processor's software architect do to design systems such that transactions can be hitting the basic server a few thousand times a second, and still whenever the transaction hits, it is understood that there will be 50% of the cases there will be an immediate follow-up call for the most recent transactions in the transaction table, and that has to be pulled out from the transaction table and shown to the merchant. So the transaction, the charge that is being done hits the transaction table as an insert, immediately followed by, within a few 5 seconds or 10 seconds, immediately followed by a query to pull out the last 10 transactions of that particular merchant. So this is a phenomenal amount of load on the transaction system when we are already talking about a few thousand transactions a second. So the first thing to do is, we know the mantra, horizontal scaling. So we need to distribute the web service load across a cluster of servers. We cannot talk about one server, okay? So the servers will be able to, the application server code will be replicated, it will be able to handle the processing load, the CPU load will be handled. What about the database? To handle the database load and to reduce the load on the database, what the architect can do is he can cache the most recent transactions in RAM. So for a particular situation, we had done some calculations where we had talked about like 100,000 active merchants and 1,000, 2,000 transactions every second, and we had come to the conclusion that for this kind of data to be cached in RAM, we will need about 50 GB of RAM. Now, when we have tremendous latency requirements, tight latency demands, 50 GB of RAM today is not a very big issue with modern servers. So what we discovered is that it is very feasible to address these challenges using the fastest storage system known to technology, which is RAM. We discovered that it is doable even though the classic architecture which is used for such situations is an architecture where the query hits the database, and we don't know why it is done this way. So if you use a cluster of servers to handle just these last 10 transactions query, so you're basically building a microservice. If you use a microservice for this, then you can use a message bus to feed this microservice from the main transaction processing server. So one server, or you can say one microserver service, will handle the transactions where the data record is inserted in the transaction table. From there, a service bus, an enterprise service bus or a message bus, call it whatever you will replicate that transaction data to the query handling microservice. So we are talking about two services here, one of which at least is a microservice, the other also can be a microservice if you want, not really, but if you want. So we have a transaction processing service and a query handling microservice, and the message bus in between is the critical link. So the transaction server will first do the transaction, it will update the transaction database. By doing the transaction here, it means it will take the data, send it to the payment switches, the payment processing switches of the payment industry. The payment processing industry have their own dedicated switches which are used to connect credit card devices, ATMs, etc., etc. The switches will send the transaction data to MasterCard or Visa or RuPay, will get clearances from the issuing bank for the card, will report back to the transaction server saying charge is done, this transaction is successful. That is what is meant by transaction server will first do the transaction. Then it will update the transaction database. After the transaction database is updated, it will post a message through the message bus to the query server. So the query microservice will get this data and keep it in RAM. Each last 10 transactions microservice will hold only the cached data of the users who have queried it recently. So there is no need for us to to prime the cache with the data of all users. At any point in time, only a few merchants, 5-10% of the merchants are alive or are active. So we need to only hold the transaction data for those merchants in the cache. If a server in this cluster, in the microservice cluster, crashes, there is no harm done. That server can be rebooted or a new instance can be started and the cache will build up over time. So when a new server starts in this cluster, it will pull data from the transaction database. But once it pulls data from that database, it will hold it in memory. It will not repeat that query again. So after the server starts up, it will rapidly get updates over its message bus. It will not do any queries to the transaction tables, and the database will never see the load of the queries. On the other hand, the microservice will literally be able to respond to the web services in a matter of microseconds, because there is no network traffic, there is no querying of a database. It is data being returned from the RAM directly. So the last 10 transaction challenge can be very effectively handled given modern hardware and large amounts of RAM simply by partitioning the roles and having a microservice which handles this query entirely from RAM. The next case study. This is very interesting. Of course, it is very interesting. Why would I give you the case study otherwise? Millions of users are querying an e-commerce system or a hotel reservation system to see available rooms or available items which match certain search criteria. Now, the database of possible hotels or the database of possible items being sold may go into millions. The number of users who are querying this system also will go into millions. So at any point in time, in any second, you're probably expecting to see thousands of queries hitting your database. Now, in such a situation, if you are going to pass on these queries to the main transaction database, your system is doomed. And this is the classic architecture which a relatively thoughtless architect will give you. So what is most important here is to have a replica database which handles these queries without loading the main transaction database. So you have to separate the query database cluster from the transaction database. That is the first. And in this situation, one of the interesting things is users will accept slightly out of date information. Look at the last 10 transaction situation. The last 10 transaction case study required, one of its key requirements was that the most recent transaction must be included in the statement. So there has to be almost zero latency. Latency has to be in microseconds. That was its constraint there. Here, that's not the constraint. Here you just need to handle very large numbers of users, very large numbers of available items for sale, SKUs. It could be items being sold like physical items being sold by Amazon, or it could be hotel rooms which the traveler is searching for, or it could be railway tickets, airline tickets, whatever. So there are a very large numbers of items and there are very large numbers of queryers, but the status does not have to be extremely low latency, which means that the replication requirements are not that tight. So in that situation, one of the things you can do is to handle the very large volumes, you can shard the data across a cluster. So you can split the data across multiple servers and do a kind of map reduce. Pass on the query to all the servers, get a response from all of them, aggregate the response and send it to the user. The other approach is to have an array of read-only databases, but each database will have the entire data set. So if you have like 10 terabytes of data, then have 5, 10, 20 replicas, 5, 10, 20 databases, each database with 10 terabytes of data, having all the records, and basically the load of the query just gets distributed, just like a load balancer concept. It gets distributed across the databases. So The first step is to replicate the data from transaction database to query databases. The second step is to spread out the query database from one database to 10 databases or 20, whatever, so that the load can be distributed. Once that happens, you can have a very large number of users or customers querying your database. You can have horizontal scalability. And one of the chief problems of horizontal scalability is not applicable in this case, and that is the tight latency. So for the sharding approach, sharding can always be done at two levels. One is at the level of databases and other is at the level of applications. So a database level sharding is done using a database software which understands sharding and hides the details completely below its API. Examples of databases which can do sharding effectively are Vitess and CockroachDB. These really can scale up to terabytes are a small figure. We are talking about very large databases, and they can handle easily several thousand queries or tens of thousands of queries per second, and they can handle the distribution of their data set across their physical data stores completely transparently. PlanetScale today, in fact, is a well-known, I think it's a unicorn in Silicon Valley, offering you a sharded database, very highly scalable database as a SaaS service on AWS. So yes, we have databases which can do sharding, or you can use databases which do not understand sharding and the application does the sharding, in which case the application code will have to have database connections kept open with each shard. So you have 10 shards, let us say, and the application code will have database connections open with each of the 10 shards and will pass on the relevant operation to the relevant shard. It can be done at the application level. So these are broadly the approaches which can be used to attack this requirement. I'm not saying it's very easy to do, but it is very feasible to come up with a design which can do this effortlessly, finally in operation. The volumes will be phenomenal, the reliability will be fairly good, and modern technology can be used without using any rocket science. So this is the second case study, and it can be addressed very well. But intelligent architects are required. An architect who understands quantified volumes, throughput, database transaction speeds, etc. Now let's look at the third one. They look similar, but they are not. The third one is something which applies to trading exchanges. Imagine a stock exchange. Say there are 2,000 different companies whose shares are traded every day. There could be 20,000 listed companies, out of which 2,000 are actively traded every day. So this stock exchange has shares of 2,000 companies actively traded, and there are 100,000 investors or 1 million investors who are buying and selling very rapidly. The scenario in stock trading has become much worse because of algorithmic trading, so the throughput requirements of orders have really shot up. So we are talking about tens of thousands of orders per second. So a stock exchange is forced to handle tens of thousands of orders hitting it every second. And these orders have to be matched. A buy order and a sell order have to be matched, and trades have to be closed, and information has to be sent back to buyer and seller. So it's an extremely high intensity, continuous heavy load operation. Of course, it also has its own peakiness. As I was saying somewhere in one of the earlier episodes, some of these trading exchanges say that 50% of the day's volume comes in half an hour. So it's a highly peaky load also. So the peak loads must be far worse than the daily average. So what do you do? The first thing to notice about such trading or such transactions is that the buying and selling of, let us say, Tata Motors shares has nothing to do with the buying and selling of SBI shares or the buying and selling of I don't know, name it, some other shares. So why is this the case? This is because if there are 100 buyers trying to buy, let us say, Jindal Steel shares and 50 sellers trying to sell those shares, they are only dealing with that one share. They don't care whether a million other buyers are buying or selling or not buying SBI shares or HDFC shares, right? Because the buyers and sellers of one item have to meet. So once you understand this, then you realize that it is not one stock exchange, it is not one trading market, it is actually 2000 trading markets, because we said there were 2000 companies whose shares are being traded. So it is 2000 completely disjoint trading markets of 2000 different items. There is no overlap between the transactions of one share and the transactions of another. So once this is understood, you can start sharding your system itself. Not just the database, but even your resources. You can split your so-called trading system into 100 or 1000 trading systems. So horizontal scalability is immediately available. So this is the first recognition, this is the first insight which allows for horizontal scalability. And at the application level, you need to look at the buy order or the sell order and know, okay, the buy order for Tata Steel shares goes here and the buy orders for SBI shares goes there, because that's where the SBI shares are being maintained and this is where the Tata Steel shares are being tracked. So the application can split the transactions at the application level without any overhead. Now, when you do sharding, you will need to have replicas of the shards just for redundancy and fault tolerance. So that is part of the overheads. And when you want to do queries, when you want to, let us say, do an overall market picture query or any other query which cuts across all these shares or all these companies, then you need to have query servers. Now, query servers will be separate servers which will receive updates from all these trading and transaction servers, and they will be maintaining an aggregate database. So separate the query database from the transaction database cluster and serve the queries from the replicas of the transaction server. That's another option. You replicate the transaction servers and use those for queries. And the third option is you use logical replication to build an aggregate database. To give you one example, we don't know what the internal architecture is, but IRCTC is India's biggest online transaction processing system. They handle railway queries, railway train ticket sales. So each train is a completely isolated world. Let me explain even more literally. The seats of the Mumbai-Delhi Rajdhani of 20th May are one world. There is no connection between those and the seats of Mumbai-Delhi Rajdhani of 21st May. Or the seats of any other train of 21st May. So every day of every train is an isolated universe. So the potential for sharding is fantastic because there is no overlap. There are no cross connections or cross data linkages. So in such a situation, IRCTC is able to do a lot of scale up, a lot of horizontal scale out, and they are able to they are aiming to do, as per one news report, they are aiming to do more than 200,000 bookings every minute. So these huge volumes may seem like scary and daunting initially, but they are not really. I mean, they can be handled with the right architecture and an insight into the data. You have to understand what connections exist and what decouplings are possible. That's where you get your opening. So now that we have sort of finished the series, I will just throw some summary thoughts at you from my slides, and there are quite a few summary thoughts, and hope to wrap up. Okay. The first parting thought. We have learnt a lot about service-oriented architecture and microservices and all sorts of other advanced things. But small and medium applications running in a single data center can happily run monolithic. You don't need to make them into a service-oriented architecture. Think about service-oriented architecture when you are exceeding a few hundred web service calls. I have deliberately kept the number vague because where to draw the line is of course very contextual. But where you have more than a few hundred web service calls and where you have very different, very divergent, very varied user profiles and usage profiles. For instance, there are human users and there are API users. And some of the largest volumes of transactions are coming from only, let us say, the API users and not the human users, and so on and so forth. So when you have a mixture of different types of usage patterns, different types of users, and you have a very large number of web service calls, then a service-oriented architecture may help you partition the overall application into more manageable pieces. Microservices are a very good idea. They can be added to both service-oriented architectures as well as monolithic architectures. Pick up the 1, 2 or 3 situations where you need extreme performance, and for each of these you dedicate an Alfa Romeo or a Lamborghini or whatever. What about a Bugatti Veyron? It may be a Bugatti Veyron. So they can be added to SOA. Which brings me to the, anyway, we'll talk about that. The next important idea is RAM and caching are both underutilized in a lot of architectures. When performance is at a premium, you need to see whether you will get a benefit by using, say, 20 gigabytes of extra RAM. Because RAM is not being used enough. A lot of read-only queries can be entirely handled from RAM. Caching is underutilized, but then caching is overutilized blindly. So on the one hand, intelligent caching is underutilized. On the other hand, blind caching is overutilized, and there are dangers there. When you overutilize caching, the keyword here is blindly. When you overutilize caching blindly, you are often unaware of the consequences. You are unaware of transaction boundaries, race conditions, or other performance bottlenecks also. So either you will get suboptimal caching or you will get good caching with other problems, unless you know exactly how the caching layer works. One more point we see is that there is insufficient understanding about non-SQL databases and non-ACID databases. I am putting them both broadly in a single very broad bucket. So a lot of software designers have got so locked into the idea of transaction boundaries and ACID databases that they just cannot comprehend things like distributed databases with eventual consistency. Now, eventual consistency is a very powerful concept to give you very high scalability. The horizontal scalability which every architect is glamour struck by is easily available if you are willing to accept distributed databases with eventual consistency. But we don't see sufficient understanding among the circle we deal with for these things. So to take that same thought a step forward, some architects over-design for absolute data correctness and absolute consistency. Very often, businesses survive very well with a small percentage of margin of error. But if I propose this to designers and architects, very often they go ballistic. Are you trying to tell me that we are going to play gambling with other people's money, etc., etc.? Extremely emotive responses come out, not from the brain, but more from some other parts of their consciousness. So they over-design for absolute consistency, and this reduces scalability. This point I think I have made before. If someone starts telling you about how fundamentally superior a pure microservices architecture is, just politely walk away. Don't try to get into a rational discussion with such people. One of the key points about architecture: there is no such thing as a best architecture. in general. There is such a thing as a right architecture for a particular context. So just like there is no such thing as a best shirt size, you need to get the shirt of the size that is right for you. Right? So there is a lot of people who are not very clear about the fundamental underlying concepts of architecture often talk in terms of, oh, that architecture approach is old and outdated. Modern architectures are all like this. They talk that language. So they talk about best, they talk about good and bad. Architecture does not allow for such evaluation at all. There is only appropriateness. Now, final thought, and this is not actually one thought, but anyway, final slide, I promise. So there is this ancient Indian belief from ancient India that knowledge exists independent of the knower. Knowledge exists, full stop. The knower is one who finds the knowledge, who discovers or uncovers the knowledge. So this appeals to me, this makes sense. So whatever I have covered in these episodes is knowledge which I have uncovered, which is in the ecosystem. It is there, shared among all the practitioners who have designed systems, all the engineers who have suffered bad architecture, and all the developers who have struggled with various implementations. So this is not a set of videos where I share my knowledge. This is a set of videos where I have put together what I have discovered and presented them hopefully in some structured way. So if I have to use the analogy of author and librarian, what I have done is the job of a librarian. I have not authored a book. This is not my knowledge. And it's very important for you to take whatever works for you without getting deeply involved with the discussion of right and wrong. Okay, what is right for a particular context is not very right for another context, and there are very few subjects which are as contextual as architecture. So I'm hoping that in all these episodes there were many bits and pieces which you might have found useful. So pick those up, and those which don't sound useful to you should be just dropped. There is really nothing much to worry about verifying the correctness of many of these perspectives. But one point I suggest you don't let go of. Architecture is built on a foundation of non-functional requirements. So this fundamental connection, the NFR provides the foundation on which architecture is done. If architecture can be called a practice, then the practice of architecture is based on a foundation of understanding of NFRs and accompanying performance benchmarking. That's about it. So we've come to the end of the series. I hope you had fun. I definitely did. And this is like a summarization of more than 2 decades of work we have done in Remigis. And we keep doing interesting things and keep figuring out interesting insights about architecture all the time. Thank you.